What I want to look at here is something called binding energy, and the questions come up. You do it in level 3, of course, and part of the reason I'm doing these videos is so that you can get up to speed, because term 4 being quite short. But I think we already looked at atomic mass units, or you should have there on the videos, and electron volts, and you know that one atomic mass unit is equal to 934 mega electron volts, and we looked at the fact that carbon-12 was used as the basis for that, and what we did was we found the mass of carbon-12, one Avogadro's number lot of carbon-12 atoms or nuclei equals 12 grams. We did the calculations, we divided through by the number of atoms or nuclei and got the mass, and we worked out this average sort of mass for a nucleon and converted that atomic mass unit into electron volts. Now the thing is though that if you actually, so one atomic mass unit, we can see that this would have each atomic mass unit being 1, this would have 12 atomic mass units. That would be its mass. That's a packed carbon nucleus with its 6 protons and neutrons, right? So you've got this packed nucleus with its 6 protons, 6 neutrons, right? And each nucleon has an average mass of 1. So per nucleon is 1 atomic mass unit. Now the thing is, if you pull this apart, all those protons and neutrons, all 12 of them, and weigh those masses separately, then you're going to end up with a bigger mass. So the mass of the parts is bigger than the mass of the whole. And the mass, and this is all related to potential energy. When we take these little particles off to the ends of the universe, they are gaining potential energy. So you gain potential energy when you have a force, well, when you work against the force. So when you lift something up against a gravitational force, that's a gain in potential energy. So when you pull this nucleus apart, you've got a gain in potential energy. You're pulling against the strong force. So this little distance here is down to about 10 to the minus 15 meters, right? So at that point, you've got this incredibly strong electrostatic repulsion between the protons, but you've got now this new third force, the strong force, which is the force of attraction within the nucleus. And so you'd have to pull against that to break the atom apart, and that would increase the potential energy. Now the thing is with that, when we pack the nucleus back together, we've got a low potential energy, low potential energy. So where'd that energy go that existed when it was separate? Well, it goes into a reduced mass. See what I'm saying? The actual energy they gain when you pull it apart results in an increased mass, and when you pack it together and you've got a decreased energy, that results in a reduced mass. And this is called your binding energy. So the bigger the binding energy, the lower the potential energy, and the smaller the mass per nucleon, right? So, but it's all based on carbon, so it goes down to 1, doesn't it, at this point? So we can end up getting these graphs, but it seems a little non-intuitive, because the bigger the binding energy, it's not really non-intuitive, it's just the words. The bigger the binding energy, then the lower the potential energy. All right. It's given up that energy, and the smaller the mass. So that's a bigger mass deficit. So if we calculate the mass when it's separated compared to when it's all together, then that's the difference, is the mass deficit. So the bigger the binding energy, the bigger the mass deficit, the lower the potential energy, the smaller the mass of the nucleus. So even some of my good students sometimes get a little bit confused with that. But what I want to show you though, just briefly, is the graph. We see this graph and it sort of looks something like that. This is Z, if you like. This is the atomic number getting bigger, and this is the binding energy. Now there's a couple of ways you can do this. Let me just reset my computer so that I can see the video. This is, we can have a couple of different scales. So up here we might be around about, I don't know, 92 or something like this. This might be where uranium is. These low elements might be where hydrogen is. And up the peak of the curve we might have iron. It's the most stable one. So these are binding energies. And the bigger the binding energy, the more stable, right? So up at this end here, we've got a binding energy of maybe 1.008 atomic mass units. So like I said before, we can do this in terms of atomic mass units, or we can do it in terms of mega electron volts. So that would come out at, I don't know, 7 to 8 mega electron volts if you do the conversion. So you can have both scales. You might have atomic mass units over there and mega electron volts over here. That would help show you what's going on. So you can see that if we were to look for carbon or something like that, then the binding energy is about that, right? Because the carbon, when it's separate, has a bunch of protons. It might be about 7.5 or something like that. And when it's together, it's got 1 for its average. So this is up around this zone here, would be around the 1.008. Things are a little more, it can be even a little bit more stable in carbon with even bigger binding energies. So the numbers we'd be looking at for those type of atoms is 7.5, 8.5 mega electron volts. And that's all based on the fact that the proton, when it's separate, has a binding has a mass of about 1.007, neutron 1.008, and that's equivalent to about 7 or 8. This is atomic mass units. That's equivalent to about 7 to 8 mega electron volts. So the thing is that we've got this loss of energy when you pack a nucleus tight. It's seen as a decrease in mass for the packed nucleus, and we call this binding energy, and we can have it in mega electron volts or atomic mass units. Now the thing is, that means that something like uranium, if it splits into 2 smaller nucleuses, there's going to be this energy release as it gets a bigger binding energy. And the same thing over here, if we get 2 smaller elements and they combine, there's going to be this energy difference, an energy release, as we get a lower potential energy, a bigger binding energy in the nuclei. So this is the fusion side, and this is the fission side. You need to know this well for scholarship, because the nuclear questions tend to be explain type questions. So I think that pretty much does it.